Okay, thank you. So MCFM has been around for a long time, almost over 20 years. In the beginning, it was constructed by, okay, let me see the point, by Keith Ellis and John Campbell, and the purpose was to sort of CDF and these areas to look at how to find the Higgs in those days at the tevatron, and this was trying to collect all the next linear order calculations in a single Monte Carlo for that process. And nowadays, with the LHC starting to study the Higgs in great detail, it's a good time to upgrade MCFM to next linear order and include all sort of Higgs relevant processes and backgrounds and things like that in there. But once you go to next linear order, you run into all kinds of numerical issues, and I will discuss these things here, how we implement next linear order and still have a reasonable evaluation time by going to multi-threading and use and distributing the computational load over large clusters. Okay, so technology, in fact, has a large impact on the Monte Carlo generators. We used to program these Monte Carlos in a non-parallel manner and heavily favoring storing to speed up evaluation over actually on-the-fly recalculation. And nowadays technology is moving very rapidly into many integrated core architecture. So now if we start using MCFM, and just, for instance, I have here my 8-core processor, and I just run 8 processes of MCFM on the CPU, then you'll see it will not work at all. Actually, you start to run slower because of, and then you can either just give up the old way and just run on big clusters, 1 process per core, or 1 process per node, or you start to think, well, what's the reason for this and how can we take advantage of all these cores on these CPUs. Once you look a bit at it, then you immediately find there's OpenMP. OpenMP has the advantage, of course, it runs parallel. It's part of the compilers, and it basically uses all the available core without user interface. It just looks whatever is available. And most importantly, it uses all the cores see the same memory and the same cache. So that means that all the these Monte Carlos, they use a lot of memory, they use a lot of memory which is the same between all the threads. So you can use shared memory to reduce the memory transfer between the CPU and the main memory. So MCF for any Monte Carlo integration uses Vegas. Vegas is a perfect structure to parallelize the Monte Carlo. Basically, you start with a grid, which is sort of the optimization for the phase space integration. Then you tell it to evaluate a certain number of events. You can distribute that over the different threads. It will evaluate these events, and then you can then you go back to the master thread to look at what it evaluated and optimize the integration grid. Then you go back and redo it. In this way, you can run very easily in parallel, and still for the optimization of the phase space integration, you use all the results from the separate threads to accomplish this. Now, once you do this and you run it, you'll immediately see that it actually works, but you have no idea whether it actually works correctly because MCFM goes back 20 years and many parts of the code which probably haven't been looked at for 20 years because it works, and now you're going to run this on a multi-threaded system, and so it's very unlikely that this all works very well. So how are you going to to debug this and make sure it all works, there are hundreds of processes in there. There's over tens of thousands of lines of code. So what you want to do, what we did is we construct a special random generator so that independent of how many threads you use, it always generates exactly the same events. So what it means is that I do not have to do a statistical comparison if I run on one thread or run on 100 threads, that it reproduces the same result. It will exactly reproduce the same number, independent of whether you're on one thread or 10 threads or 200 threads. And that way you can very easily see where things go wrong. And then once you do that, of course, you see that most things go wrong, and then you have to really start looking at all the individual processes and find what goes wrong. There's a lot of, because you use shared memory, there's a lot of writing to that shared memory, and often the threads will write to the same memory location and you get problems. Now once you have debugged that all, then you can finally start looking at some how it all works. So I did here for 4 different configurations to calculate, as an example, PP to Higgs plus 2J at the next leading order. First on a regular average desktop CPU, which has 4 cores, runs at high clock frequency and has a lot of cache. Then a motherboard with 2 Intel processors for a total of 12 cores. Then a quadruple AMD, a motherboard with a quadruple AMD processors with a total of 32 core, and also on a Xeon Phi. I only use an older Xeon Phi. There are now newer ones which are much faster. But that shouldn't make any difference for the better. So first you can look at leading order with a very modest number of events. And under the perfect circumstances, then if I use twice as many threads, you expect it to run close to twice as fast. What's showing here first is just a single processor, Intel 4-core. You can see it scales nicely up to 4. After 4, it uses hyper-threading, so it still speeds up at a bit slower, so that works fine. Here's the dual-core Intel motherboard, and you see it scales almost perfectly up to its 12 cores. The AMD scales nicely, but here it starts to break down. In fact, the AMD has the same cache as the Intel, but it has many more threads. And you see here it goes wrong. So here the process is no longer, the time is no longer dominated by the actual execution time, but it's dominated by memory transfer. All the threads are waiting for memory to get to cache and back. So and then the more threads used, the more sort of everything starts to collide and the whole system breaks down. The Xeon Phi is here on top. It also starts to scales nicely up till it starts to get into memory-bound issues again. So basically, leading order, what you actually calculate is not very complicated. So you're bound to run quickly into memory-bound issues. So if you give it next to leading order, it has much more to calculate, and the memory issues will be much reduced. So here you can see these ones already scaled nicely, but now you see that the 4 processor AMD card or node will also scales also very nicely up to the full 32 threads, and also the Xeon Phi here scales up nicely. You see a break at 64, and there's another break at 128 where it sort of does a bit of hyper-threading. I don't know exactly the technologies there, and but this is a very old card, and the newer card probably perform both time-wise and much better than this example. So now with all this multi-threading and using OpenMP, you can actually use a next leading order on a workstation. For instance, here we look at PP to 4 jets, where 2 of the jets come from the Higgs decay. If you use like 150 million events at leading order, that if you take this dual core, this 2 times 6 core Intel node, you only need like 12 minutes to evaluate this, and you can see here the result. You get very smooth results. So leading order on these runs extremely fast. Next leading order, I ran here for 22 hours, and you can see here the results you get. And this is just on a desktop or a workstation. There's no big cluster involved, and you can get very good results. Now you might think, why do I need all this? Well, if you want to do next leading order, the first requirement is you need very fast and accurate next leading order, because the next leading order is part of the full next leading order, but you have to evaluate many more events than you normally do for next leading order calculation to integrate to do the phase-space integrations. So now that we have sped up next leading order, we can look at next leading order. So MCFM has already hundreds of processes already built in a next leading order, and we can reuse these to upgrade the Monte Carlo to next leading order. Now to combine next leading order with the two-loop virtual contributions which have been calculated by other theorists, we need some way of combining it, and basically you have to isolate the soft collinear part of the next leading order, integrate and combine that with the virtual so that you get finite cross-section. And here we use the slicing method. Here we use the so-called jettiness subtraction, non-local jettiness subtraction, which is a slicing method. And there's the advantage that all the slicing functions already have been calculated by people who do effective field theory and SCAT. And this method is very similar to the QT subtraction method. However, QT subtraction doesn't easily work for jet final states, while the jettiness subtraction method works for jet final states without any problem. What you actually do is you isolate a single region, which is soft radiation and collinear radiation, with a cut, and then below the cut you calculate the contribution analytically, ignoring terms which vanish as the cut parameter goes to 0. So this calculation is valid in the limit of that you choose this cut parameter small. Then you combine that with virtual and you obtain a finite analytic function, which is a logarithmic dependence on this tau cut. And then above the cut you add in the hard phase space numerically, and then you have to, and then the cut dependence will cancel and you get a finite answer. And this is valid for very small tau cuts. You can see here all these people who over many years calculated all these slicing functions for your jet functions, beam jet functions and things like that, and these you can all combine to get the next leading order predictions. So here's, for instance, a very simple, here's an example. If you want to calculate next leading order PP to vector boson plus jet, you use already the existing MCFM next leading order PP to vector boson plus 2 jets. And instead of demanding 2 jets, you now demand 1 jet. This will produce it that one of the jets basically can become soft or collinear, which produces a singularity. This is regulated by this jettiness slicing cut. And then you can add these slicing functions to the virtual, combine everything, and you get the next order prediction. Now to use next leading order, you cannot really use that on your workstation. You have to go to a cluster. So to further distribute the events, we use MPI. So and this again fits nicely in the Vegas framework. So Vegas has its initial grid, then MPI will give the grid to each of the nodes in the cluster, and then each of the nodes will have to evaluate a certain number of events, and there OpenMP will distribute it over each of the threads of the processors in each node, and then it's all collected back in the end. The grid is optimized, and it goes through this whole cycle again. Now, OpenMP works it's part of the compiler. It works very easily. You don't have to really think about it. MPI, what we have, is a bit more complicated. It seems to depend a bit on the cluster itself. And while it works fine for us, some people have experienced other problems with it. And so it's a bit more tinkering than we want, but there's not really any alternative to it. Now, how does this work? So here, we simply do PP to W plus, and this is leading order, next leading order, next leading order. This is the evaluation time. This is the number of cores we used. And this uses a cluster of 24 nodes, each containing 2 processors of 6 cores. There are 2 running modes I can use because the node contains 2 processors of 6 cores. I can use 1 MPI job bits, and then the OpenMP will use the 12 cores as in one unit, or you can use 2 MPI processors where each processor on itself will parallelize, but they're independent of the other processor. You can see here, if you look at leading order, for instance, this is using 2 MPI processors per node. That works better than using 1 MPI processor per node, and the reason is, of course, that the cache is physically separated between the 2 processors, and it has to synchronize them if you use it as one OpenMP process. So it's better to use 1 MPI process per CPU. And you can see here that, again, at leading order, because there's not that much to calculate, if you scale up the number of cores, it starts to level off, and it becomes memory bound, no longer scales properly. Next leading order, it scales a bit further, but eventually it also starts to level off. Next leading order has much more to calculate, and it nicely scales, and it will scale for a long time before it starts to become a memory bound problem. Now, this is all the processes included in the MCFM, in the first release of MCFM. That's WZ, Higgs, Higgs W, Higgs Z, gamma gamma, at next leading order. And here you can see how it scales. This is again the number of times. This is a number of MPI jobs. Each MPI job is with 6 cores, and this uses about 10 million events. And you can see that all the processes scale nicely. You see a bit of turnover for the Higgs, but this is the simplest process to calculate of all of them. And it will, yeah. So here you can see sort of, this again with of the order of 10 million events, how much the time it is on this 48 core, on 48 cores. You can see the times in seconds here, and this is the statistical error you're going to find when you run it. So, and the statistical error depends on this tau cut you use. However, you want to use a smaller tau cut because you neglected terms which are finite in this tau cut. So there's a sort of balance of where you want to choose this tau cut. Here you can see the dependence on this tau cut. This is the next leading order correction, and this this is for the W plus production, so you know the analytic answer, or you also the analytic answer. And you can see sort of how, as you choose tau cut smaller and smaller, it converges to the right answer. Same here for W Higgs. So you have to think a bit of how to choose this tau cut. What is done in MCFM, we've preset certain values which we looked at these processes. If you want a 1% error due to this tau cut, which is basically a systematic error, you can choose a 1% or 0.2% error. And then you want your statistical error to be not smaller than this tau cut, but sort of a bit larger. So you're not dominated by the systematics, but you're dominated by the statistical error. And that way you can run without much issues. I'll skip this for time reasons. We go to what we are planning for MCFM. So apart from adding more and more processes, there are many planned improvements for MCFM. One improvement is this slicing method itself. We had all these power corrections, and you had to worry about how small do you choose this slicing parameter. This can be improved by actually including more of these powers of these terms analytically. Another one is improving phase space integrations. Here, basically, you want to separate phase space in the leading order times an extra piece, which is the branch volume, and then you unweight leading order. And for each of the unweighted leading order events, you're going to calculate the next leading order weight, or it's actually either in k-factor weight or in distribution, depending on how you do the clustering of the jets. And that way you can optimize phase space dramatically. We're also working on including partial shower matching for all the processes in MCFM at leading order, next leading order, and next leading order, and this will be matched to PITIA. You can employ GPUs for double branch trial and tree-level phase space integrations. And here, at the moment, it can only basically handle one PDF set, because a PDF set comes with a large grid, which uses a lot of memory. If you use multiple, like for error PDFs, you maybe use 40 PDFs, you'll see the whole scaling with the number of threads will be broken, and you will have no acceleration. So you want to replace basically these grids by on-the-fly PDF evolution. So improve slicing, you can see that happening here. So usually here you see the normal one, which is now in MCFM. You can calculate these points. You see here the dependence. You can fit to it, and you get this curve. Now, if I include this term, these people right here calculated this term analytically. If you calculate that analytically, you get dramatically different behavior, and you can use this slicing cut much larger. And choosing the slicing cut much larger means a much faster. You don't need that much events, so your evaluation time will speed up considerably. So this particular method holds great promise, but because it seems you cannot only calculate this first term, you can start to calculate the second term, the third term, and in principle, you can start to calculate the exact phase space integration up to a certain cut in a truncated series, and in that case, you can use this cut as large as you want, and you just and then there are really no problems anymore with the slicing method. I will skip this, and I'll go to the conclusions. So we extended MCFM to provide a public code for next leading order processes using Jetina slicing. We use a hybrid OpenMP MPI version to make next leading order MCFM fast enough to run on small to moderate clusters. You don't need huge resources. Currently included is Higgs production, WZ, W Higgs, Z Higgs, and diphoton. Processes which are already existing, but we're working on it to include it. Is Higgs plus jet, W plus jet, Z plus jet, photon plus jet, WW and ZZ, which hopefully will appear there in the coming year. And we work on many methods to improve it. the leading power corrections, including leading power corrections, novel phase-based methods to improve the phase-based integration. These things are really needed for these processes with jets, which currently need enormous resources to evaluate. And with these two improvements, we will get this working on very reasonable clusters of a few hundred cores. We are matching MCFM to the PTS shower, both at next linear order and next linear order. And we are thinking of using GPUs for the double param spelling, which is all tree-level, to achieve next linear order back to desktops and along on clusters. Okay, thank you.
Thank you very much. Time for questions. I can get started. So you mentioned you have a method to calculate random numbers.
Yes.
Seeing whether or not you use microprocessors. So how does that work? To explain.
Yes, so what you don't want is a different seed for each thread. Right? So we basically want the same sequence of random numbers in bunches, because to generate your momenta, you use a certain number of events. So basically you want to make sure, so you do sort of, you know how many threads you have, so you can sort of skip your random number generator ahead, depending on which thread you are. So it skips a certain.
Okay, so each thread has to know how many other threads there is.
It knows, yeah. And then you make sure it generates the same sequences of events. It's a bit hard to. I can explain it earlier.
More questions?
So just looking at your web page, it seems that this is written in Fortran 90. Is that correct?
It's a mixture that goes back 20 years. So there are parts which are very old Fortran. There's Fortran 90. There are also C parts, C++ parts. It's a whole. But the main part is now Fortran 90. Yes.
So I think that most experimentalists live in the C++ world. Is there any thought about moving into a coherent, say, C++ code base?
No, that would be an enormous task. But, I mean, a modern compiler doesn't really care about Fortran or C. It will just happily combine and compile without any issues. Well. Oh.
That's a quick question. So you want to use GPU to
Yes.
the four-part database. I would say that's the easiest part of the next order part. Harder part for the subtractions. So is that really going to save the day by doing the easiest part much quicker than leaving the hard?
It's also the most time-consuming part. Yes. You spend most of the time doing tree-level. Because the phase space is simply the largest.
Okay,
So it.
The genus.
Yeah. And with GPUs, you gain accelerations of order a few hundred over CPU.
Thank you very much.
Yeah.